Okay, hello to everybody. So I accept the question once more about components or connected components, which is they are synonymous for a graph. And let's see, the notion which is important is this. In a graph, we say that U and V are said to be connected if there is a UV path in G, so a path having U as origin and V in terminus, or conversely, because we are in the undirected case. So if you have a path from U to V, you also have the inverse path from V to U, okay? And you also accept that there is a path of zero length. So every vertex is connected to itself by just staying there, so to say. So the idea of connected for a graph is very easy. You can go from every vertex to every other vertex through the edges of the graph, okay? But you might have that it's not always possible to do that. And so that you have pieces, so to say, different pieces of the graph, okay? And how can we identify these pieces which are called components? Well, the book introduces these pieces, the components, as the equivalence classes of this relation. The relation of being connected is an equivalence class. Every equivalence is an equivalence relation. Every equivalence relations produces what is called a partition in its set, meaning that if you take the equivalence class of each element, if you have an equivalence relation, then you get some subsets of the original set, such that the union of all these sets is the whole set, and that they are mutually disjoint. Okay, but I also gave a different way of thinking of that. Take, for instance, this graph. This is the whole of all this which I'm circling is one graph, okay? But it has three components. And how can you see these components? By picking up, for instance, some vertices. Say I take these three vertices. If I take these three vertices and these two edges, is this subgraph connected? Yes, because from any vertex of these three to any other vertex of these three, I can find a path. So this subgraph here is connected. Is it a component? No. Why? Because there is a bigger subgraph of the original graph, which also is connected, and it is this. So if you want to understand what a component is, or connected components is the same thing, it is a maximal subgraph which is connected. If I only add also even this, then it's no more connected. Why? Because this has no path leading to from here to here or to here. Same thing if I add this vertex or these two vertices. You don't have any path from here to here, okay? And what if I take, say, these two vertices and this edge? This is also a subgraph which is connected, but it's not a component. Why? Because there is a bigger subgraph, this one, which is still connected. If I take these three vertices and these four edges, is this a component? Yes. Why? Because it is a connected subgraph. And there is no bigger subgraph of the original graph which is still connected. If you add to these three vertices any one of these vertices, you do not get a connected subgraph. Why? Because, for instance, from here to here, there is no path in the graph. Maybe the problem is to look at the definition of walk and then of path. and well understanding what a walk in a graph is, and then the idea of path is easy because it's a walk with no repetition of the vertices. But now I cannot stay anymore on this, I'm sorry. Okay, let's go to this. I had said I would not talk about these two exercises. Instead, I want to say something about these two exercises. This one shows that every tree with exactly two vertices of degree 1 is a path is not so difficult, apart from the fact that it looks too easy and one could not know how to start proving it because it's too immediate and too intuitive. And too intuitive things in graph theory are dangerous because maybe you do not find immediately a way to prove. A way to prove this is, let's start with what we have. G, a tree, with exactly two vertices of degree 1. Okay, and so I want to show path. Let me try, sorry, with this other part. Okay, so what do we have? Let U, V be the vertices of degree 1. Necessarily, all other vertices have degree 2, because if I take the sum of all degrees, Vi in the set of vertices of the degree of the I, this is what it is, we know from a proposition, it is twice the number of edges, but the number of edges in a tree is ni minus 1, so this is 2 ni minus 2, okay? And since if we had only one vertex of degree 3, then we would necessarily have, because of this, not just 2, but at least 3 vertices of degree 1. Okay? So necessarily, all other vertices, apart from U and V, must have degree 2. Okay, so we now do like this. We build out our path in the sense that, no, let's go to the next page. So, start with U. There is exactly one vertex joint to it phi, because U has degree 1, so there is only one edge coming out of it, and so only one vertex adjacent to it. Okay? Call it V1. Apart from U, there is only one vertex joined to V1. Okay? Why? Because V1 has degree 2, so one of its adjacency is just for U, and so we just have another one, okay? Call it V2. Having reached a vertex H minus 1, it is joined to VH minus 2 and is joined to only another vertex call it VH. We are forming a path U, V1, V2, VH. Eventually, we must reach also V, the only other vertex of the degree 1. Because the graph is finite. May I change page? G is finite. No vertex has been left off because otherwise it would belong to a different component. So it was good to go over this notional component again, to a different component. And this is impossible because G is a 3, so it is connected. Okay, let's have a look at the other, which is much more complicated because the other one is a bit difficult to understand as to understand what the problem wants, okay?
Professor,
I mean,
can you reread what you have write and explain it more.
Okay. Okay. We know that there are. We have a. What do we have? This is what we know. What is given. G is a tree, so it is with no cycles and connected, and with exactly two vertices of degree 1. First thing, since it is a tree, epsilon equals ni minus 1. So twice epsilon is 2 ni minus 2, and this is the sum of all degrees. So since two vertices have degree 1, all others must have degree exactly 2. Okay? So we know that when we reach a vertex, either it is a vertex of degree 2 or it is that other vertex of degree 1. This is what I do. I start with one of the two of degree 1. Say I start with you, and I build a path starting from u, which will end with v, and will leave no vertex out of this path. Let's see how. We start with u. U has degree 1, so there is only one vertex joined to it. Call it v1. Now, what about v1? v1 is connected with u, and it has degree 2, so there is exactly one other vertex joined to v1. Call it v2, and put it in our path. And then and we go so on and so forth. For v2, we are coming from v1, and so one valency of v2 is occupied by v1, but it has degree 2, so there is another vertex adjacent to v2. Call it v3, and so on and so forth. Assume that you have gone like this up to vh minus 1 with our building of a path. Then it is joined to VH minus 2, and it has another valency open, and so we have only another vertex joined to it, which we call VH. So we are forming a path. We go on. Necessarily, since this is, well, if this were an infinite graph, and we do not talk about infinite graphs in this course, in this book, then we could go on forever, but not with the finite graph. With the finite graph, you have go short of vertices. Eventually, you reach the vertex, the other vertex of degree 1, and you finish your path. One could say, maybe you have left out some vertices of degree 2. You have built a path, and it's okay, but maybe it does not cover all the graph. And I say, yes, it does. Why? Because we have, in the vertices of the path, we have occupied all valencies of all vertices. Okay, so there is no other vertex joined to one of the vertices we have in the path. So if there were other vertices in G, they would belong to a different component. This is impossible because of what we know. G is a tree, but what is a tree? It is a connected acyclic graph, and so it cannot have more than one component. It has just one component, and so when we reach the other vertex of degree 1, we are sure that we have finished all vertices, and so our graph is a path. Okay? But if we have difficulties with this, then absolutely get rid of this. Forget about 218. It is probably too difficult. Okay? So let's go on with our theory. Okay. We have seen this this wonderful recursion procedure for finding what the number of spanning trees is in a given graph. Okay, we know from the work of the mathematician Cayley that if we have a complete graph, we can directly say that the number of spanning trees of it is n raised to n minus 2. Okay. If you want, try to draw the 16 spanning trees of K4, which is a good exercise. But let's go to the connector problem. This is, in a certain sense, a more rational problem than the one we saw with dice-graphs. Because we have a graph, a weighted graph again, and if we can think of the weights as we had discussed this last time, simply length of roads or cost of the motorways or time to travel or discomfort or whatever, okay? And you might want to minimize the connection. Meaning what? Meaning that we want to have a subgraph of the given graph by which you can reach from any town, from any vertex, any other vertex. Not only, but that the total sum of the weights of the selected edges is minimal is the minimum possible with respect to that particular weighted graph. Okay, the paradigm is this of having towns, cities, and wanting to connect them by an optimal connector. Optimal in the sense that you want that the total number of miles that you have in your network is the least possible by knowing what the distances are. Okay, these are the true distances between London, Mexico City, New York, Paris, Peking, and Tokyo. Okay, and so of course you can connect everything with everything else, but it costs a lot in terms of fuel for the aircrafts. Okay, so if you want to have surely connection so that you can go from Peking to Mexico City surely, but with the least possible number of miles, then you must do what is called an optimal connector. Okay, you might have that you do something strange like here actually Tokyo and Peking are directly connected, but well, New York and Mexico City as well. Okay, but you might have that you have to do a long several change of airplanes. Everybody who has traveled and had little money maybe has done this. Okay, let's take 24 hours and 2 changes of aircraft, but I want to spend very, very little. Okay, it is possible that for going from here to, say, Budapest, which is not so far, I might have two changes of airplane if I want to spend very little. Okay, but the idea is you can go from everywhere to everywhere, but we want to spend the least possible fuel, and so have the total weight, which is the least as little as possible. It is different from the problem we had with Dijkstra's algorithm, because in that case, you were not interested in connecting everything in the best way, but in connecting one particular place to every other with optimization focused on that particular vertex. This is the difference I want to hear when I ask you the difference between these two problems and these two algorithms at the axon. Okay? It's useless to repeat two algorithms if you don't understand why one, why the other. Okay, let's see what the algorithm is like. It's Kruskal's algorithm, and it's very simple. Start with the link E such that the weight of E1 such that the weight of E1 is as small as possible. Now, assume that we have already, and it's recursive, okay? Recursion is very, very frequent in combinatorial constructions, as much as induction is very, very frequent in combinatorial proof, okay? So we assume that we have already chosen E edges. Now we have to choose the next one. How to choose it? Choose ei plus 1 from the remaining edges in such a way that two things occur. One, if you add that edge, you don't close a cycle, and among the edges which assure you that you do not close cycles, you take one which has the smallest possible weight. Okay, and then you stop when you cannot do you cannot go over. Okay, and it's possible to prove, but it's out of our aim to prove that if you do this, if you use Kruskal's algorithm, you get what? An optimal tree. Okay, let's see how it works in this case. Okay, we have this, which is the graph representing this situation. And again, these edges are straight line edges, but it does not mean that you have a straight line from one to the other, okay? You might need to do with your aircraft a different generally it is an arc of a greatest circle, but that's not important. We just say these are there is a possibility to have an an aircraft going from Mexico City to London, and it would have 56 100 miles, okay, and so on. So what do? We start with the or one of the edges with the minimum weight. And here there is a wonderful 2, and so of course we pick up 2 immediately. Okay? Now let's look for another edge with a small weight on it. Okay? And the smallest one among the remaining ones is this between Tokyo and Peking, 13. Can we add it? Yes. Why? Because if we add it to the one we had already chosen, we do not close the cycle. Okay. So now we have these two. It's something which did not occur with dice crust. Do you remember? We always had connection with dice crust. It's different as a problem and also as a way of solving. Okay, we have these two. Let's see what we have, okay? We have, for instance, this 21, which appears to be the least weight of the remaining ones. Can we add it? Yes, because it does not close a cycle. Okay. So, next, what do we have? Next, we have 35 is actually... Yes, 35 is actually the smallest. Can we add it? Yes, because adding it does not close a cycle, okay? And next, the next smallest would be 36, okay? But if we add 36, we close a cycle. And why is it silly? Why shouldn't we do it? Because if we close a cycle, it means that we have two different ways of reaching Paris from London, and this is a stupid thing since we already have one, okay? And or reaching New York from Paris, okay? It is longer from Paris to New York to go through London because it's 2 plus 35, while directly it would be 36. Still, there is a path from Paris to New York, and so we keep it. We do not want to have a double situation. This would add fuel to what we have to spend. And so we do not put 36, even if it is the smallest available. Next, after 36, we have 2 with the 51. It could be this, and it could be also this. We can choose either, and so the authors have chosen this. They could also have chosen that. Okay, no problem. Why? Because both have the smallest weight and of the remaining edges, and the addition of either does not close a cycle. And so what we get is finally a spanning tree. Also Dijkstra's algorithm yields a spanning tree, but in a different way. Here we get a spanning tree, and surely we have the least possible total weight. Okay? Please do this. Start back with this and do Dijkstra's starting from Mexico City. Okay? You'll see that you'll get a different spanning tree, okay, which will be optimized for Mexico City, not optimized in general, okay? After having solved Dijkstra's for Mexico City, make the sum of all weights. You'll see that surely you'll get a bigger sum than what you get out of this, okay? But if you are in Mexico City, it would maybe better for you to have that for going to Peking, you just spend 78, 80 instead of spending 21 plus 35 plus 51. Okay, which is what you would do if you were in Mexico City and would use this particular greedy airline, which makes an optimal connector. Okay, so, okay, and these two are surely in your midterm test. All right, nothing more in this chapter.
Excuse me, Professor.
Tell me.
In figure number 2.11, the down and at the right, yes, this one. Why they used the edge? They used the edge between PE and PA. I mean, that's the number as the same as 51.
Yeah, because they had to choose one, okay? And it was indifferent to choose one or the other, okay? So they had to choose one, and I think it was very good that they put now the need of a choice. You don't put them both. You have a choice to do in this moment. As I said, you could very well, instead of this, add this, but not also this. Instead of this, add this, okay?
Yes.
And it would
There is
be
no important that which one.
no. Why? Because both would add 51 to our sum. So exactly the same number. And neither of them closes a cycle. This is important. And so you could choose this, you could choose that. Okay, be an engineer, be an engineer. Being an engineer means that choices are scarcely random, okay? And so you start with some constraints, and then the constraints that your customer says is, please build me an optimal connector, okay? And this would be very good. Since you have a choice, what is Paris? Okay. Since you are given only these constraints, so it would be indifferent from the mathematical viewpoint to do this or to do this, okay? But if you have a choice, as an engineer and not a mathematician, what would you do? You would find another constraint which was not given to you in order to make a smart choice. For instance, you know that your boss, the person who pays you, is French, then you would probably add this, which would be a little better for a French person, okay? It's not a constraint given from the beginning, but as an engineer, if you have a choice, find, this is my suggestion, find a further constraint which helps you to make a choice, not a random choice, but a smart choice. Okay? And I say that as a mathematician, so you know it's difficult for me to say what an engineer should do. Anyway, I think this is what an engineer should do. Adding constraints, okay? It is something that you do, let me also say that when I teach at the first year linear algebra, I have this very important theory of linear systems, okay? There is someone who knows that I do these things, okay? Okay, linear systems often have infinitely many solutions. Infinitely many solutions is something very nice for a mathematician, and which is a bit troublesome for an engineer. Okay, it could be very well a very good answer, because you might be interested in a qualitative answer, and knowing infinite instead of one qualitatively could be very important. It represents the stability of the scaffold. Then you want that just one solution is there. If you have infinitely many, it means that it would collapse. So if you look for something qualitative, infinite is as good as anything, okay? But if you want to find the solution and you have infinitely many, you do not, as a mathematician, they are all alike. But for an engineer, you should find something which makes a choice smarter than another one. And so what does an engineer often do? He or she builds a norm, okay? A norm so that among your infinitely many solutions, you find the one which minimizes that norm. Don't forget this, even if it is coherent with other things than graph theory. Anyway, if you have choices, find a way to make a smart choice and not a random one. End of this part. Let's go to the next very, very short chapter, which is connectivity. They start by saying, okay, you already know what connection is, what a connected graph is, and actually what is minimally connected, as we have seen, is a tree. Okay, if we have a tree, it is connected, and even if you, and we know that every edge is a cut edge. So destroying, canceling, deleting one edge would surely disconnect the graph. Okay. I must tell you a little bit of history of this. All this part, which we treat in a few minutes, was very important and was invented by the Allies in World War II, okay? Because they had this problem. You may know that Germany had invaded quite a big part of Europe, okay, and was menacing of invading also Great Britain, okay? And the Allies went to Normandy with their forces, okay, and they had terrible losses, of course, because they were on the beach, and the Germans had all the continent, and so it was very hard for them, above all, to get to all the logistic to get ammunition, food, medicals, anything, okay, because everything was across the channel, so it was in the island, and they were on the beach and a bit more of the beach and a bit more, but the Germans had Germany directly connected to the front, okay, and so they had this problem that they had to interrupt the connection between home Germany and the front. The front was in France, and so there was still a way to go for ammunitions and everything from Germany to the front. And so they wanted to disconnect the communications from Germany to the front. Okay, and they had to do it in the best possible way, in the sense saving. Okay, I used to do, and I also can do now, a sort of a joke by saying that probably they had many Scottish researchers in this, because we know that Scotsmen are very cautious with money, okay, and not very many Americans, because Americans love bombing, as we know in Italy, because every month or so, after 70 years, we still find unexploded bombs, always American bombs in Italy, every month, 70 years, but every month you hear, okay, tomorrow at noon, all this quarter has to be evacuated because they have to take out an American bomb of World War II. Okay, I said they love bombing. And I said that, and there were two young people from Montenegro, and they said, we know very well how Americans love bombing, because they had also experienced that. Okay, so anyway, jokes apart, you have to understand how you could efficiently disconnect a graph, okay? What to delete in order to make a connected graph disconnected. And so the branch of graph theory called connectivity was built exactly in that period, okay? And so we already have the notion of edge cut and of cut edge and of cut vertex. Now we can also introduce others, but the very smartly the authors show you these four graphs, okay, which are one inside the other, and you obviously see that you have qualitative, intuitive idea of greater and greater connection, okay, from here to here. Here, of course, it's the maximally connected graph with these five vertices, and this is one of the spanning trees. It is a minimally connected, okay? Delete the edge you want, you don't interrupt connections here. Delete any edge, you interrupt connections here. And so you have different stages. How can we formalize these different stages of connectivity? We have two notions, which are connectivity and edge connectivity. Let's see what it's about, okay? A vertex cut of a graph G is a subset V prime of V, such that if you take, they should say of a connected graph G. It's not well written in this part, okay? They should say we have a connected, I don't see that they have said that anywhere. They should say, let's take a connected graph G, okay? And then a vertex cut is a subset such that if you take away these vertices, then what you get is disconnected. A K vertex cut is a vertex cut with K vertices. A complete graph has surely no vertex cut, okay? If you take a complete graph, if you delete this vertex, okay, this vertex is deleted, okay, but you do not disconnect the graph. Okay, are you with me? Okay, so it is never disconnected by deletion of a vertex or two vertices or three vertices. Whatever is left in a complete graph is surely connected. Okay. But, okay, complete graph has no vertex cut. In fact, the only graphs which do not have vertex cuts are those that contain complete graphs, a spanning subgraph, meaning they could be not simple graphs, meaning that they might be complete graphs plus some loops plus some multiple edges, okay? But if they contain a spanning subgraph, which is complete spanning, I recall spanning subgraph, a subgraph which reaches all vertices of the original graph, okay? So the only one which have no vertex cut at all are those which contain complete graphs as spanning subgraphs. If there is at least one pair of distinct non-adjacent vertices, so that your graph does not contain a spanning subgraph which is complete, then we call connectivity with this, again, a Greek letter kappa. Connectivity kappa of G is the minimum K for which G has a K vertex cut. Otherwise, if you have a graph which contains a complete spanning subgraph, we say that kappa of G is ni minus 1. So we, by convention, even if we do not have any vertex cut here, we say that the connectivity of this complete graph is 4. Okay? All right. Thus, kappa of G equals 0 if G is either trivial, which means just one vertex and whatever you want on that vertex, or disconnected. If it is disconnected, it is already disconnected. You do not need to delete any vertex to make it disconnected. Okay? G is said to be K-connected if kappa of G is greater than or equal to K. All non-trivial connected graphs are necessarily one-connected, meaning that if you at least one connected, they should say at least K connected, so they are at least one connected. Okay, so the number that you have, that it is K connected with K greater than or equal to 1. This should be said in a proper way. Now let's go to edge cuts. Edge cuts were already defined in the previous chapter. I recall how they are. An edge cut is a subset of E, is a set of edges in this form. What does this form mean? Two things to say. If I put here two sets of vertices, when I put brackets around two sets of vertices, I mean the set of all edges which have one end in the first and the other end in the second set. Okay? And here, what do we have? S a non-empty proper subset of V, S bar the complement, meaning all the other vertices. So here we have a certain set of vertices, and here we have all the other vertices. None of those has to be empty, okay? And bracket for those means the set of all edges having one end in S and the other end in S bar, okay? A K edge cut is an edge cut of K elements. If G is non-trivial, again, not just one vertex, and E prime is an edge cut of G, if we take E prime away, we get a disconnected graph, okay? We then define the edge connectivity kappa prime of G to be the minimum K for which G has a K edge cut. For a trivial G, again meaning just one vertex, kappa prime of G is defined to be 0. So kappa prime of G equals 0 if G is either trivial or disconnected as before. And kappa prime of G equals 1, at least 1 if, no, exactly 1 if G is a connected graph having a cut edge. Because a cut edge by itself, the set containing just a cut edge, if a cut edge exists, is by itself an edge cut. Okay? And G is said to be K edge connected if kappa prime of G is greater than or equal to K. All non-trivial connected graphs are one edge connected, meaning that kappa prime of G is at least 1. Okay? Before going to this theorem, of which I do not give anyway any proof, let's see what happens here, and then we have a break. Here, of course, delete any vertex of these two, and you disconnect the graph. Okay, so this by itself is a vertex cut. This by itself is a vertex cut. Here, again, we have a vertex cut, which is given by this cut vertex, okay? And here deleting one vertex is not enough to disconnect the graph. What do we need? We need to delete at least 3. Say these 3 or these 3. And then if you delete these 3, then you get that you disconnect this vertex from this. Okay, and here, as we have already said, deleting any vertex does not disconnect the graph. What about edges? Here, the deletion of one edge is enough to disconnect. Here, one edge is not enough. If you delete one edge, it's not enough, but it's enough to delete these two, for instance, or these two, or also these two. Even if you leave one isolated vertex, this means anyway disconnecting. And here 2 is not enough, okay? You need at least 3, say, to delete these 3 edges, okay? And here, of course, you need 4 edges to delete if you want to disconnect the graph, okay? Now, okay, it's easy to state the theorem. It is this. Kappa is less than or equal to kappa prime, which is less than or equal to small delta. Okay? But please, my friends, when you repeat, because you have a very good memory, you repeat this very easy statement, please do know what kappa prime, and above all, what small delta is. Of course, if I ask you, okay, you correctly remember this inequality. What is small delta? And you don't know, I must reject you. Not because you do not know small delta, but because you speak of something which you do not know what it is. And this is not admitted for an engineer. Okay? So this is what we have. We'll have a look at this particular graph just to see what happens here, and then we will go on. But 1804, let's say 1805, 1815, I start again.